So as the topic goes, that is the geoprocessing using Python. So, so before going into the geoprocessing, we should have some understanding of the geospatial technology. What does it consist of? Very two important aspect which I will be covering. There are many other terms also, but the two most important which are used for the geoprocessing, they are remote sensing and geographical information system. I will be taking you to the various aspects of remote sensing in terms of the data, what kind of data is there, and what kind of processings are performed on top of these kinds of data sets. From where do we get these data sets? Whether these data sets are proprietary in nature or they are freely available, some sources for the data download. Similar is for the geographical information system also. I will give you one small demo on how to download the data set from some freely available sources. Like one is very popular free open that remote sensing data or the satellite images, that is the Bhuvan Geo portal. From there we can download one small satellite image, and then we can understand how the data looks like and what are the various features of that data sets. So if the content basically is geospatial technology, who are those users and what are the various applications that are inherent with this geospatial technology? Definition of remote sensing in GIS, data sources and data analysis part. So the objective of this session is to make you aware about the data types and the processings involved in geoprocessing and visualization. The basic objective is to make you understand about the data types. So if we talk about the geospatial technology, it enables us to acquire location specific data about Earth and use them for analysis, modeling, simulation and visualization. It consists of two major technologies, or three, I will call three major technologies associated with it. The first one is remote sensing, second one is geographic information system, and the third one is satellite navigation, that positioning and the timing information that we get from the satellites. How do we get it? But the focus of this lecture will be on remote sensing and GIS. So if we talk about remote sensing, there we have various sensors operating in different parts of electromagnetic region at various spatial, temporal and spectral resolution. What are these spatial, temporal and spectral resolutions? I will be covering later on in the slide, because these are the typical characteristics of a remote sensing data. You should be aware of these terminologies. Similarly, for GIS, if we talk, we will talking about spatial data creation, updation, visualization, and analysis. Secondly, having known about these three technologies, who are the people who are using these technologies and for what purpose? Some examples to cite over here. An urban planner, he might want to access the extent of urban fringes, where this urban is growing in his study, in his city, and quantify the population growth that some suburbs are witnessing. He might also like to understand why these particular suburbs are growing and their others not. So this is one query that comes to the mind of an urban planner. Yes, he can solve these problems using geospatial technology. He can automate all these tasks, the tasks associated in this one, through the geospatial technology. A biologist, he may be interested in the impact of slash and burn practices on population of amphibian species in the forest of a mountain range to obtain a better understanding of long-term threat to those populations. Similarly, a natural hazard, another type of another domain, natural hazard analyst. For natural hazards also it is used. You want to identify what are the high-risk areas of annual monsoon-related flooding by investigating the rainfall pattern and the terrain characteristics. Similarly, a geological engineer, he want to identify which are the best localities for the construction of building in an earthquake-prone area by looking at the rock formation characteristics. So by looking on this area, how to identify which are the best localities. This comes under the study of site suitability analysis. Similarly, a mining engineer, he might be interested to determine which are the prospect copper mine or some other kind of mine that should be selected for future exploration, taking into account the parameters like extent, depth, quality of the ore, and many others. Similarly, a geoinformatics engineer hired by a telecommunication company, he wants to determine the best site for the company's relay station, where to establish these kinds of relay stations, and what parameters he will take into account, like cost factors such as land prices, undulation of the terrain, and many others. So one more, another domain, that is the forest manager or a hydrological engineer. This is forest manager. He may be interested in timber processing, how to optimize the timber production using the data on soil and current stand distribution in the presence of a number of operational constraints such as the need to preserve species diversity in the area. Similarly, a hydrological engineer, he wants to study a number of water quality of different sites in freshwater lake to improve the understanding of the current distribution of, let us say, reed bed and why it differs from that of a decade ago. Now, this temporal studies that also can be very easily performed using our GIS techniques. So having known about who are the users and for what purpose they are using it, let us talk about what is remote sensing. Some basic concepts only I will be covering. I will not go into the detail. What is remote sensing? You can see from this picture, the ultimate source of energy is our sun. Now, between the sun and the earth, there comes an atmosphere also. So the sun's energy coming through this atmosphere interacts with various features on the surface of earth. They act as a target. Now from here, the energy is divided into, undergoes three processes. The first one is absorption. Some of the energy is absorbed by this feature. Some of the energy is reflected and some of the energy is transferred also. Okay. So the energy which is reflected from these earth surface features, they go back to the atmosphere and there are the eye on the space. That is called a sensor. A satellite, it is having one sensor. You can see over here, one small sensor we have put it. Now what these sensors are doing, they are receiving these reflected energy from the surface of earth and they are recording it and reproducing them in the form of an image. So we can say remote sensing is the art, science and technology of obtaining information about an object or an area from a distance. What is that distance? From this space. Okay. Typically from aircraft, or it can be a satellite also. I can mount my sensor on top of a satellite, on top of an aircraft. More recently, we are also mounting our sensors on top of a drone also, or a UAV. Now there are two types of remote sensing, we call it. First is the active remote sensing and another one is passive remote sensing. We will not go much into the detail of it. So these differ in the term whether we are using the sun's energy or we are supplying the energy from the sensor itself. Suppose let us say microwave remote sensing. So I am giving the energy to it and I am recording back the reflected energy. So the difference is only on the source of energy. If the source of energy, whether the source of energy is the sun or the source of energy is from the sensor itself, like radar and all those things, lidar or radar, anything. So once the data is received, they are acquisite and processing stations are there in this particular receiving station. From there, the data are passed on for the analysis. Once the data is analyzed, they are analyzed for various applications, the application which we have seen earlier also. Similarly, if we talk about GIS, it is also a computer-based system that provides the following four set of capabilities to handle geo-reference data. You remember it. What is this GIS? It is basically a system only for the capture and preparation of geo-referenced data, the data which has location information inbuilt into it. Similarly, it also allows data management, including the storage and maintenance. It should also allow data manipulation and analysis. And lastly, it should also allow the functionality for the presentation of the data or the visualization of the data, how the data can be visualized. If we talk about now this is very important slide over here. What is the fundamental principle of geospatial technologies? What are those things that we cover up? So the problem of spatio-temporal problem. Okay, so this aspect, the spatio-temporal problem, these are basically addressed by the geospatial technology. If you see, in most of the applications we have seen earlier, there was a spatial component. Spatial means with respect to the location. He wanted to identify which are the best places for timber production, or which are the best places for identifying a suitable hydropower site. So space is playing an important role in that. At which place, like suppose a market, suppose there is one production company, a company which generates some product, a manufacturing company. They are manufacturing some product. Now they want to identify which are the places where these products can be sold out, or before that also, which are the places where we can set up a manufacturing industry. That will again depend upon the supply of raw materials and meeting the demand of the users who will use those products manufactured by the company. So space is playing an important role over there. Temporal, again, over the period of time, how the dynamics have changed. So the temporal phenomena, that also we will not go into much of detail of it. So these two aspects are basically touched upon in the geospatial technology. If I talk about geospatial data, how it looks, because in geoprocessing we will be talking only for geospatial data only, how to handle, how to cater with these kinds of data sets. So a geospatial data, it is a geographically referenced data that describes both location and characteristics of the feature. If you see in the figure over here, I am seeing one tree over here. Okay, now there are two important characteristics for this tree. First is location of this tree. Where is this tree? Okay, and what is this tree and what are the attributes of this tree? So these two, location information and attribute information. So we divide them like these two parts. Okay, now we will see how this can be later in the coming slides. I will tell you how to store these kinds of data sets. What are the various forms, or what are the various formats of the data storage for this kind of geospatial data set. Now, some of the sources of the input data for geoprocessing, from where I will get these data sets. What are the things? What are the tools or techniques through which this geospatial data is collected? If you can see it here, I have various sources from where I can collect the geospatial data. It is from the remote sensing. This remote sensing, which I told you earlier, it becomes a very important source for a geospatial database. All the satellite images or aerial images or the UAV images, they are nothing but input for the geospatial technology. Okay. Similarly, through photogrammetry, this is again measurement from the photographs. So what we do, we take a photographs and do some sorts of processing on top of, we can say, photogrammetrical processes, and it gets converted to specific images. Sometimes we call them images as terrain corrected images. Terrain corrected images means, suppose there is one satellite image and I am doing some measurements on top of it. If I am able to do the measurement, it becomes a georeferenced image. But suppose there are some hills also, and I want to measure distance between two places. So it will give me a planar distance. Suppose I have corrected the data in such a form that even that hill is also taken into account. So that kind of processing are performed in photogrammetry. They provide us orthophotographs. So they also act as a geospatial data, as an input for the geospatial. Similarly, GNSS, this is a very generic term for GPS, which you call as a GPS. So, but the generic term is GNSS, Global Navigation Satellite System. Now, this is basically a group of satellite, a constellation of satellite, which provides us the location information, the coordinates that are coming from this particular system. There are some surveying methods also, ground surveying method. They also provide they also act as input source for geospatial data. Hard copy maps, many times through there is one agency called Survey of India. They are also producing some maps, some hard copy maps they are producing. So we can take those maps also as an input for geospatial data. Similarly, the laser methods, ALTM, they are also one important source of data set for geoprocessing. Now, how do we represent these kinds of data sets? So, the computer representation of the geospatial phenomena comes in two formats basically. First, we call it as a raster data model, and the second one we call as vector data model. Okay, if you can see it here, this is your real world phenomena, and in GIS or the geospatial, we divide them, we represent it in the form, either in the form of a vector or in the form of a raster. You can see it here. Raster is basically a grid-based data structure. The smallest element of raster data model is a pixel. And some of the examples are satellite image, aerial photographs, or maps. So these represent the raster data model. You can see it here. In computer, you will be seeing it in the form of a grid here. It is one grid, and I have different colors. These colors are nothing but these are the pixel values representing different features. Let us say this particular series of pixels are representing some forested land, and some blue pixels, these are representing some water body. Similarly, this red one, it is representing some urban settlement. Okay, so it may be having some different pixel value. So your computer does not see the color, it is seeing the value associated with this particular pixel which it takes for processing. Okay, and there's a difference in the pixels also. Now we can use any random color for depicting that particular pixel. If you see it here, the second, the vector data model, basically it is a geometry based model or the structure. So here the basic elements are point, line, or the polygon. Examples, if you say roads are represented as line, boundaries like city, country, or the building footprints, they are represented as vector data model. If you can see it over here, so I have a coordinate system here. Now this particular point, it has the x coordinate and the y coordinate. Similarly, a series of points forms a line, whereas a series of points with start point and end point at the same place, it becomes a polygon. For me, the starting point and the end point are the same, then it forms a closed polygon. If they are different, then it forms a linear feature, or a we can say curvilinear, or it forms a line feature basically. Now, if we talk about, again, I will come into the raster data model, more into raster data model. If you see it here, I have another kind, not only satellite images. Suppose I have a map in which this particular portion is represented by some cornfield. This is some, we can say, land use map. And here there is some wheat area. And here I have the fruits. Or again, here it is the some cultivation, fruit cultivation is going on. Similarly, here clover or some other crop is there. Now all these features, if you see here, they are represented by different kinds of number over here. If you see it here, this fruit, it is represented by this number called 4. So in my grid, wherever I am getting 4, that means it is a fruit. So I have to create one lookup table also. I should have one lookup table also, in wherein these numbers are referenced also. Okay, what does this number represent? Okay, or I can have a cluster also, a cluster of number 2, cluster of number 1, cluster number of 3, cluster of number 5, and these clusters can then be given some names also. Okay, Now here each and every cell, sometimes they are also called as a pixel or the picture element. So they form raster data, often called the image data. This raster data is also known as an image data. Now what are the attributes for it? Attributes are recorded by assigning each cell a single value based on the majority of the feature in the cell, such as the land use. Now suppose the size of this grid is, let us say, 30 meter. In 30 meter by 30 meter there may be many features in the ground. Okay, now whatever is the maximum, that is represented by this particular, the majority of that feature will represent that entire 30 meter by 30 meter area. Now similarly for the vector data model, if you see it here, it has an XY value pair and a label with it. Okay, lines is a series of points. Similarly, area lines forming their own boundaries. So this again, I will just move forward. So now for each and every, now here in the raster data format, we were having only one pixel value. But in case of a vector, I can maintain a separate table also, which saves not only the geometry, but also various attributes also can also be saved in that particular table. We will see one example also of it, how they look like this. Now if you compare this raster data model and vector data model, so here the location is referenced by a grid cell in a rectangular array. Attributes, they are represented as a single value for that pixel. Much of the data, it comes from the images of remote sensing or the scanned map or the elevation data from some agency. It can be ISRO, it can be US, it can be anything. Now this raster data model is best suited for continuous features like elevation or temperature. Suppose I want to represent this temperature phenomena in a through a map, then I can go for the raster data model, a continuous feature, how they are varying. So similarly for the vector data model, they are basically best suitable if with discrete boundaries. Suppose there are certain features which have discrete boundaries like roads or political boundaries or sometimes building footprint. So these are the best features which are represented using the vector data model. Now let us come more into the digital images, because this term they will be used in your future classes where many times these kinds of words will be used for you. They will be useful for you. If we talk about what is a digital image, it is a grid or a pixel of cells like this. Okay. Now this is one image I am seeing. It can be any image. Okay, this one image is displayed over here, and this particular small portion I have zoomed it here. So once it is zoomed, so in this there are many pixels. This is one pixel. Okay, now your computer does not see these as a shades of gray. It is seeing them as a array of numbers like this. All numbers are there only, but you will see it like this in the zoom form. But the computer see the same image in the form of digital numbers. So these numbers are of great importance for you. Henceforth, whenever you will be working with geoprocessing, so these numbers plays an important role. Now, some of the characteristics of the image data. These are image data set. They are geographically referenced. Geographically referenced means the data is in sync with the ground coordinate. It helps us in making the measurements on top of this image. Yeah, if you see it here, I am seeing one satellite image. Okay, and this image, there is one playground. I have drawn one polygon on top of it, and I am getting some area. So if you see this area, 18057.446 square meter, around 1 hectare. So this is 1 hectares of area. How I am able to get it? I am measuring on the image, and I am getting the area of the ground, not of the area of the picture of the image. This is all possible because your image is geographically referenced. So keep in mind, whenever you are doing geoprocessing, your image should not be a plain photograph. It is a geographically referenced image. it should have some geographical information inbuilt into it, embedded into it, in its header or somewhere else. Okay, so this becomes very much important. So we need to take only geographically referenced images, because if I am doing some automatic analysis, or some implementation of some geospatial analysis automatically, and I want to overlay 2 or 3 images. So if those images belongs to the same area, you know, and they have the same geographical referencing embedded into it, then only I will be able to reference one pixel of one image with another pixel of the another image at the same location. Suppose let us take. I will take a new example here. This I am interested to see whether these trees over here, they are permanent or they have changed over the period of time. So for that, I will be requiring one satellite image of, let us say, X year, and another satellite image of, let us say, Y year. So I should have the same image. Okay. Now, if these images are geographically referenced in the same coordinate system, then I can write some program which will automatically correlate the pixel of this particular image X with the pixel of the image Y at the same location. Then only it will be able to do it. Okay, so you bear in mind that geographical referencing is very important in case of georeferenced images. Then only we are able to do some measurements or any kind of processing. So this particular aspect is very important. So although there are various techniques, there are separate lecture for this, how do we reference a geographical image. So but you will be getting it for this particular course. You will always be getting one georeferenced image along with you. Only thing is that you need to take care that this georeferencing is same in various images which you are taking for a particular task. Okay, so the terms which you will be using, they are called EPSG codes for the referencing system, like European Petroleum Survey Group. So they have devised some codes also, like this one particular code 3857. This assigns the WGS pseudo Mercator, spherical Mercator, or the Google Map, OpenStreet, Bing Map, ArcGIS Map. These are some of the use cases where this code has been used. You will also be try to see the first task what you to do. Whenever an image is given to you, you try to see what is the EPSG code of this image. Try to extract it through some code. So I think in the coming lecture, Ravi sir will be telling to you how to read the geographical information of the image. What is the projection system of the image? So most of the time you will get those information in the form of codes only. Now if I talk 3857, this is a pseudo Mercator projection system, and the unit is meter, means the image, whatever measurements you will do, the outputs you will get, the output of the measurement you will get in terms of meters only. Similarly, there is another referencing system that is called 4326. This is a world geodetic system, and it is used basically in the GPS. Whenever you are talking about the latitudes and longitudes, so these latitudes and longitudes are nothing but they are the coordinate system then the unit of measurement is degrees. Okay, so there the measurement is degrees only. Latitudes and longitude, they are not the planimetry, but they are the angular coordinate systems. Okay, this latitudes and longitude. So now more detail on. So I was talking about this spectral band also. Okay, so be careful now. Second exercise which you must do, you must try to see what are the various number of spectral bands in your image, and try to visualize these bands using different combination. This is a false color composite. If you can see, it is a true color composite. So you can try these different kinds of combinations. 3 to 1, I am using red gun of the computer. I am using for the infrared, and this similarly this green gun of the computer for the green channel of this image. Similarly, the last one also, third one, for the blue channel, the band number 1 I am using, and I am getting this kind of composite. Similarly, if you use 432, so this kind of composite is I am getting over there. So these different combinations you should try. This is the true color composite. How I am getting the true color composite. This you can try, or you can try for this false color composites also. We can have n number of false color composites, wherein we are not using the exact color which is on the ground. If you see it here, I am seeing this red image, red part. All these red is nothing but a vegetation part, vegetation section. And since now why I have used this red, because 4 is my infrared region. Okay, now this infrared region I don't have any color, so I have chosen the color red to display it. The red gun of your computer is used for displaying this infrared. And third band, and similarly the second band, the 3. So basically we have the 3 color guns in your computer. All these 3 color guns, and we can assign different multiple spectral different spectral bands to this color gun for generating these kinds of image composites. Okay, now third is, it is also very much dependent on the image pixel size. If you see it here, I have one image of 4:4 kilometer. This image content is dependent on the image pixel size. This information also you should try to extract from an image. What is the size of a pixel? What is pixel? Pixel is the smallest element of that image, one grid. What is the size of it? Now, if you see here, we have taken the one ocean color monitor satellite image I have taken over here, and this is one small portion. So A is a scene from this ocean, and this small area is 4 kilometer by 4 kilometer area. If I am seeing it here, and the size of this particular image, 1 pixel, is 360 meter. Now 4 by 4 kilometer area, if I want to visualize, it is coming like this. Now this same 4 by 4 kilometer area, if I see in 188 meter pixel size images, that is the WIPS, wide field sensor. Okay, in this, if you are saying, I am able to see some feature. Similarly, it is a 72 meter pixel size, that is a LIS1 image of IRS satellites. IRS, Indian Remote Sensing Satellite. There is one sensor called LIS3. From there, I have taken this image. Size of 1 pixel is 72 meter, and this entire image size is 4 kilometer by 4 kilometer, and 1 pixel is 72 meter. Correct? So that 4 kilometer by 4 kilometer, that is called the swath of that image. Okay, extent, we can say extent of the image, whereas 72 meter is known as the pixel size of the image. Okay, this is the pixel size of the image. Similarly, if you see it here, there is a finer resolution, 36 meter of LIS2 sensor. Similarly, I have 23 meter LIS3 image here. So better, the same feature here. Now 5.8 meter IRS-1C pan data. So here I am seeing more features over here. You can see this water body here, and this the same water body over here, and this particular feature is more sharp in this higher resolution satellite image. So the point is that the information content is dependent on the size of the pixel. Okay, so if you see it here, I am seeing a larger area, so I am seeing features at a very broad level, but I want to see the image, the feature at a very large scale, at a very minute level, at 4 kilometer by 4 kilometer area. Then I need these kinds of high resolution images. So what you have to do, whenever you take a pixel or you take an image, you get some image, and you try to extract what is the size of the pixel of that image. Okay, 1 pixel ka size kya hai, that you try to identify. Similarly, another important characteristic is image pixel depth. That is the radiometry. How many shades have been used for representing 1 pixel? It describes the actual information content in an image. If you see it here, 1 bit means only 2 colors are used. Similarly, 2 bit, there are 4 colors are used. 3 bits, I think there are 9 colors are used. Similarly, for 4 bits, 16 colors are used for representing 1 pixel. I have these many colors. The range is from 0 to 1 here. In 2 it is 0 to 3. So I have these many numbers. So if my image, the radiometry or the pixel depth is less, then I have lesser control on the information representation. If this depth is high, then I have better control for information representation. If you see it here, 256 color, how nicely I am able to see, like 7-bit image. Okay, then information is quite clearly visible. 16 color, a little bit haze is there. Similarly, 2-color image, so only black and white image I am getting it. Only 2 colors are there for representing the features on the ground. So these all play a very crucial role in case of geospatial data processing. Pixel value, now see, they also vary with respect to time also, the temporal. What is the date of pass of that image? The same image which you are seeing over here. This is some permanent feature, they are always red. You can see it here also red, but this particular section, just beside this river, there is red, it is seen over here, whereas in the image of February 2009, it is seen green. Here I have the vegetation cover. Here I don't have the vegetation cover. Okay, it is now leaf fall season over here. So that's why the image color is different. So this is how the pixel value changes with the change on the ground. There is something change happens in the ground. It is immediately reflected in the pixel value, and same are represented in the form of image as well. So as we can see in these two images. So these temporal changes also play important role in geo processing. Take account of these kinds of aspects also into it. Okay. Now, if we talk about the same things are true with your vector data sets also. They also have the important features like what is the coordinate system along with it, how and what is the age of that data, when that data was retrieved or when extracted from these satellite images. Let us say temporal. Suppose I want to represent this boundary. Okay, I have drawn one boundary from this image and I am saying ki it is a vegetation cover. This is, but it is in 2009. But if the same boundary I overlay over here and I see there is something else. So you should attach these kinds of changes also in the vector data set also as an attribute. Okay, this is vector data is of which date. That lineage of the vector data is also very important. Now, if we talk about the analysis, the vector and the raster based analysis, what kind of analysis we do? Okay, this will come more when in the coming lecture series. You will be knowing more onto these things also. The first one, vector based analysis. The first is the map overlay, the union operations, intersect operation, point in polygon, line in polygon, or polygon in polygon. So these are some of the operations that are performed on the vector based data sets. Similarly, map manipulation, dissolve, clip, append, eliminate, update, erase, split. These are the map manipulation. I am changing the map now here. I am extracting a small portion from the image. Clip. I am doing a clip of it. Suppose I have a population data of the entire country and I want only the population density of my city. So how to extract it? I will clip it from that boundary and I will get the data for my own area. Dissolve. Dissolve means making the data set similar with respect to a particular attribute. Suppose there are 10 polygons and all have the same attribute. So I don't want to represent them by different polygon boundaries. I want only one polygon for them. So I will dissolve them together. So all these boundaries are dissolved and I have one polygon only. This, but for the other attribute, I may require it also. I may not require to dissolve. So dissolve is again dependent upon the attribute. So these all will be coming in your coming sessions as well. Proximity analysis, very important here. Buffer analysis, multiple ring analysis, point distance, buffer analysis. Suppose I want to find out the location which are near to a stream or a river. I am interested to suppose there is one. I want to build a house, but that house should be far away from the river. So the distance from the river, how to convert this information into a data, distance from the river. So what we can do, we can create a buffer around the river. So this buffer information, buffer data set, it will act as a proximity data set for me, as a distance from the river it will act for me. I can have multiple ring also, like some features at a distance of 10 kilometers, 10 meters, 50 meters, 100 meters. So I can have multiple rings also. This all will be there. Similarly, the pattern analysis, nearest neighbor analysis, spatial autocorrelation, and we have network analysis called shortest route. So these all will be covered, or you should attempt it through your own codes as well. For raster weight analysis, we have local focal information, zonal information, and the global as well. Local means local you can say I am drawing one small kernel or one small grid, 3 by 3 grid, and I am running this 3 by 3 grid in the entire image. First, starting from the left corner, and this 3 by 3 kernel is moving in the entire image and manipulating the pixels based upon those kernel or the 3 by 3 grid. This is very important when we do the neighborhood analysis. Let us say how the fire will spread. I want to find out a fire event has occurred, and I want to simulate in which direction this spread of fire will be occurring. So in that case, we can say, suppose one pixel is burning at next time period, it will act as an input for the another pixel, which can take the fire input from here and start burning if there is a fuel. So slowly we have to move our image or the kernel from one portion of the image to the entire portion. So focal, again, if I am dividing my image into different sections, so that comes under the focal and the zonal analysis. Global, if I am doing some operation in the entire image, let us say multiplying the image by a number 10. So that kind of the operation which are performed in the entire image, they are known as the global image, global function. Map algebra, we can do Boolean operations over there, relational, arithmetic. Similarly, the mathematical, logarithmic, arithmetic. These all operations, they are very much possible on that grid data or the image data. Trigonometric, power, terrain analysis. Suppose I want to derive a contour map, slope map, aspect map, or the hillside, viewside. These all are done or performed on top of a raster-based data set. Hydrological analysis, flow direction, flow accumulation, stream order, watershed delineation. So these all are performed. These are, now I will move this part here. Let us take one example. Overlay operation for the layers. Now here I have, this is one map, map A, and this is another map B. So this is one vector map, you can say. This is one boundary. This is some feature A1 and this is some feature A2. In map B, I am having 4 features. So how, if I am doing the union of these 2 maps, okay, so I will get this kind of map. If you see, the geometry is changed. Now I will be having some new features also over here, like C1, C2, C4, C5, and C8. So these all features are there, and the corresponding attribute table will look like this. It will have the feature from both the map A as well as from map B, and the number of features will also increase. Here I have 2 features. Here I was having 1, 2, 3, 4 features, but in the output I am having 6 features are there. So it has done all the intersection of the geometry over, or the geometrical features in both the map A and map B. For the raster, now if you see, this is one map A and I have one map B, some pixels. Now I want to convert this map C I am creating, the zonal, the global operation I am applying. Map A plus 10, I am adding 10 to all the values for a particular operation. So it gives me like this, a zonal operation or a global operation. Similarly, map B, in this map B, now I am creating map C1, this particular map, map A plus map B, add these 2 maps, adding of these 2 layers. Okay, this is done, so one map C1 is created. Similarly, I can have some other mathematical operations also. Map C2. How this is created? You subtract these two images, map A, map B, add them, and then divide them and multiply by 100. So any kind of expression that is also done on top of these grid data sets or the satellite images or image data set. This is the output I am getting. Now, if you see here, there is one map called land use map. That is the forest here. The green part is the forest over here, and slope is equal to steep. Two operations we are seeing. I want, this is my land use map. In this land use map, if you see, this is dark green is the forest, and this light green is some grassland, red is some urban area, and this is some agricultural land. So I have different colors for different classes. Similarly, in the slope map, I have the feature, this red portion, this not red, we can say this magenta, this orange color. Over these are the steep slopes, red is some moderate slope, and these are the flat lands. Now, I want to extract the forest which is lies in the steep slope. I want to get the forest which is in steep slope. So what we will do? We will do an AND operation of these two maps. And once the AND operation is done, then we can fire that query, and this map is obtained here. So these are the forest land which occur in steep slope. So this kind of operation you should try with your geo processing in the coming lecture. So take all these things from here, and you have to do this also. Similarly, the terrain visualization. This is one elevation map or the height map, we can say. Sometimes we also call it as digital elevation model. Okay, so this is the map. Here each pixel is representing height of that location. Okay, now from this we can create this shaded relief here. Okay, applying some algorithm like same similar kind of operation or the expression, I am getting this kind of relief map, adding some value to it, subtracting something and dividing something, and getting doing some kind of map algebra, and this kind of map is operated. And now here I can clearly see if this is some hilly area and this is some flat land. So shaded relief is obtained from there. Now the same image, if I visualize using some 3D software, it is visualized like this one. Here you can see. Now, from terrain analysis, some other aspects are also there. We can extract the information like slope, aspect, surface curvature, break in slope analysis can be done. Water set already or I have covered. Some only for the reference purpose it has been kept over here. Now, I will take another example here. One geospatial workflow, one map I want to generate. So I have one soil map here. Similarly, I have the water bodies here. I have depth to water table. I have the land use map here. Means this each pixel is representing the type of feature on the ground. This yellow portion you can see these are the agriculture, and green you can see they are the forest land. Blue you can see they are the water body. Now I have these different kinds of map, and I want to perform some integrated geospatial analysis. So this is one cadastral map also there. Some cadastral boundaries are also there. Cadastral boundaries means the field boundaries we can say. These boundaries values are also available with us. Now taking all these things together, I want to perform some sort of geospatial workflow. So I can take for geoprocessing, we take the input from different themes on different themes, and then these can be combined together as we have done in this previous example I showed you here. So these are nothing map A and map B, they are nothing but these are map A, map B, map C, map D and map E, and you can create any map by manipulating the pixel value behind these maps. This was, let us take one example for groundwater prospect zoning if I want to do. Okay, so there are the factors like recharge condition, geological structure, geomorphology, rock type. So these are some of the factors, and you integrate them together, and identification of potential zones for groundwater, And we can also do identification of priority zones for constructing recharge structure. So using these data sets, I can create these kinds of maps. This is the entire methodology. I will leave this slides for you also to study them further. This was landslide hazard map. Suppose I want to create this kind of map. So what are the causative element? Base map, lithology map, geomorphology map, slope, aspect, soil, drainage, lineament, land use. These are the different maps that has been generated. Now combining them together, I can create one hazard map. This will tell me at which places there is less hazard, which places there is high hazard. If you see it here, simple additive weighing of the layer. This can be done. Simple. This is one layer. Multiply with some weight, and then add them together. You divide the summation with the summation of the weights, and you will get this map. Okay. So if you see it here, the green moderate. This is the moderate danger zone. Very low. This orange color. These are very low danger zone with respect to landslides. So these kinds of maps are created using these simple mathematical operations. Now, if we talk about how we do it, so for that there are existing softwares are there, some proprietary softwares, and there are some open source softwares also, and there are some free softwares also. But they all have their own limitations and advantages. So what you have to do, whereas because sometimes if you go for some proprietary software, that will only be a black box for you. There is nothing much is for you to play with the algorithm. Some algorithms are already, some code has been written and you are just using it. Suppose you want to add on with your own idea, you want to put to the data set. So how to put that data? So for that, you require some sorts of coding. And some coding environment or the background of the coding, how to code these kinds of data sets. So although they also provide some sorts of customization within themselves, but that is not enough for the understanding purpose. If you want to do a clear understanding of geospatial technique, then you should start from the scratch, from the coding part. Although you can use it, these kinds of software, but I will always advise you code yourself for any application and use it. Now changing emphasis from data to the analysis. Earlier in the past, most of the time that goes to the data conversion, very less part were with the analysis part. But in the current scenario, I already have data analysis ready. The analysis ready data is available with me. Now only thing is we need to perform analysis on top of that ready-made data sets. So we have reached up to this level now. Now some of the sources from where we can download the data set. This is Bhuvan portal from where we can download the satellite images. It also provides the features of 3D visualization, 2D visualization, data for the downloading, and there is a mobile app is there. Thematic services are also there, the data as a service. Now this is again new concept is coming, how to utilize the data as a service. The data is available in the form of a API. Now I want to use it in my own code. So Bhuvan provides you the facility to download the data or to access the data as a service as well. Similarly, we have India IIRS portal, BIS portal is there. These all list is there. I will be leaving this list for you. You can go through all from where we can download the data set. Now, some of the popular data formats. I have not talked about the data format. In the raster data, if you talk, you will be facing these kinds of terms will come to you, like GeoTIFF images or the NetCDF images or the HDF images or the IMG images. These are some of the formats in which the raster data exists. They have their own limitations and their own advantages also. GeoTIFF for the smaller images, suppose I have a very multi-dimensional data set. In that case, we go for the NetCDF. Similarly, if I have a very heavy data set, let us say very large satellite images there. So in that case, we go for this IMG format also. This is proprietary, but there are tools which allows you to visualize this data in open platform also. Similarly, for the vector data, you will be encountering the terms like SafeFile, which is a very popular, very open data format in which most of the data is available in this format only. Similarly, WKT is another format, text-like format. KML is another format for the vector data, GeoJSON, and of course, we can also store these vector data in a database table as well. So the database table is something called PostGIS. It has one extension called PostGIS, wherein I can store the data sets in vector format also. Now, I will quickly take you to the Bhuvan Geo portal, from where I will download one data set and then we can see it here. We will see it here, bhuvan.nrc.gov.in. I will have one open data archive. How I want to just show you how the data set looks like now. Satellite data. If you see it here, I want the list 3 data. Okay. And one example I will take one example of Dehradun region area. Dehradun, suppose I type it here, but search that data set for me, and so let us take any one slide, any one data set we can take. So I will take one data set. This is Dehradun region over here. Now here I will take this particular image of list 3. Okay. So interactive drawing. I will just wanted to show you how the data looks like basically. The objective is to show you the data. If you download how the data will look like. Select it here, next. Now if you see, it is a temporality of the data. You see the same data set is available in different time periods: 23rd October 2008, 31st March 2011, and 5th April 2019. So data set is available in different months also and different years also. Now for this 2019, I have the data of March and April. Similarly, for the year 2018, we have different data set: January, May, and November. 3 season data we have. January season, in the month of May, summer season, and then November, the autumn season. So 3 seasons data set I have. Now the features on the grounds are varying based upon the season of the upon the season. So whichever season is suitable to me, I will take the similar kind of data. Let us say if I am interested towards the wheat crop, or the crop analysis I want to do. So I will take the data of the month of November, or even later than that, or January I will take it. Because at that time that wheat crop is there on the ground. So again, it is context dependent which kind of data you are taking. Suppose you are interested only in the urban area, then this may not be this season may not be of importance to you. So you can take any data for that, but it should be cloud free. So let us take one data set of 2019 of 12th March. Okay, click it and you can view it here. It will show you this is the data set here. Okay, it will look like this only. Now I will try to download this data. Okay, so for downloading I need to log in. So I will log in. So more you will learn in your coming lectures about how to code all these things. Okay, so it is logged in now. You can see it is there. Now let us try to download this data set. So data is now downloaded. A small data set only. So in folder. Now here we can see this all you will do through data visualization extract here. Somewhere I'm extracting it also. Once the data is extracted, now you can see what the data comes in. The data will always in any format. If you see it here, I have 3 different bands: band 2, band 3, band 4, and band 5. Okay. So the data is available in 5 bands. Okay, suppose you have a composite image, then you should write some code to identify what is the number of spectral bands available in that image. Now let us try to see it. Although I will not use any code, but you will be using some code to visualize this data set. So let us say this is one image. This is some software I am using, QGIS. When I open those software only. Now here I am trying to visualize this data set. If you see it here, this is the first band, second, third, and fourth. Okay. So let us try to zoom it to the layer. So if you see it here, now the same which I was showing to you, this is band number, and one by one we will see the band. This is the first band. This is the image which displays is band number 5. Okay, this is band 5, and I switch it off. This is band number 4. You see it is the band number 4, and this one is band number 3, and we have band number 2 also. So here the features are not very much clear. The contrast is very low. Okay, whereas in case of band number 5, I have a higher contrast. Means pixel values are at a higher end in this case. You see it here, the range of values is from 1 to 664 in this particular image. That again depends upon the radiometry, how many sets we have used it. Similarly, for this band 4, I have 44 to 974. For band, it is 26 to 961. There are some higher values also, this 961. So this 961 is nothing but this cloud region over here. If you see it here, there are some white pixels also over this pixel. So these are small pixels here. One pixels I am seeing. Now I can check the values of each and every pixel. Suppose I click it here. If you see, the pixel value is 509. Here also I am having the pixel value of 534 and some darker value, dark pixel. If you see, it is 144. So there is a very quite visible change. The brighter the pixel, higher is the pixel value with it. Okay. So this all you will be doing with your Python programs now. Okay. I will not go into much of taking to the software part. The thing is now you have to code in Python for various kind of data visualization or the data analysis. Okay. So I hope I have made my point clear in this lecture. If you have any queries, you can post it